A very pleasant greeting I bid to our external examiner, Mr. Sharil Anwar, and our supervisor, Dr. Azizul Buang. We are from Group 13, and the group members are Frederick Ching Sechan, Yeo Kaizi, Muhammad Fazli bin Sharudin, Shazali bin Abdul Halid, and Teresalin Jumitol. For our plant design project, our group will be presenting on the monetization of crude refinery and waste via pyrolysis of oily sludge and modified solvay. The outline of our presentation will be divided into 6 parts, which are introduction, conceptual design, heat integration, process instrumentation and control, safety and loss prevention, and lastly, conclusion. Moving on to the first chapter, I, Muhammad Fazli, myself will explain the problem statement and objective of our case study. We will also present our finding based on the literature review conducted. For our case study, we were given 3 types of industrial effluent, which are oily water, oily surface water, and ballast water. This effluent contain high amount of BOD and COD due to the presence of oil, phenols, and sulfides, which can kill aquatic life by rapidly depleting the dissolved oxygen inside water. Furthermore, the discharge material must also satisfy the limits stated in Malaysian Environmental Quality, Sewage and Industrial Effluent Regulation 2009. Other than the environmental impact and the regulation requirement, the recovery of oily sludge and chloride from the industrial effluent also can be profitable by converting them into valuable products. Based on the problem statement, our objective for this project are first, to design a chemical plant to convert oily sludge and chloride into value-added product, and second, to ensure final discharge limit adhere to local EQA standard for industrial effluent. Our scope of work will include conducting literature review on process technologies and product markets, evaluating several process routes based on economic viability, environmental sustainability and safety consideration, and performing material balance calculation and generate PFD and PNID for constructed process design. Shazani bin Abdul Halid will be explaining about the next part, which is literature review.
Thank you, Fazli. Now, I will continue the presentation with the market analysis part. There will be a total of 8 products that will be produced from this plant, 6 from pyrolysis and 2 from modified solvay. The first one is hydrogen. As you can see the figure in hydrogen part, there are 3 major applications for hydrogen in the current market, which are methanol production, ammonia production, and petroleum refinery. Nowadays, hydrogen can be served as a green fuel as it releases only water vapor during combustion in the presence of air. According to Statistica 2020, the projected global demand for hydrogen as energy is set at 78 exajoule, equivalent to 21 billion megawatt per hour by 2050. The second one is carbon monoxide. This gas can produce hydroformylation that manufacture detergent by reacting with hydrogen gas and alkene. Carbon monoxide also can be converted into methanol through Fischer-Tropsch process. Based on the Global Info research, the global market of carbon monoxide is expected to reach 4,600 million in 2024, with predicted CAGR of over 5%. Next is carbon dioxide. This type of gas had been widely used in a modern medicine, where it served as a vasodilator for the skin during surgery. According to Grand View Research in 2019, the global CO2 market was worth 7.66 billion USD, and it is projected to grow at a revenue-based CAGR of 3.4% over the forecast period. Both figures of carbon monoxide and carbon dioxide show a significant increment over the years in the market size. The next product is methane. According to Market Research Future 2021, methane had been used in a few applications including gasoline, natural gas, and chemical feedstock. Based on the report from Statistic MRC, global methane market was evaluated at 88.55 billion in 2017. Another product from pyrolysis process is biocrude. This product has the main constituent, which is homologous phenolic compound and contain up to 20% of water according to BASU 2013. Based on the report from Energy Industry Review 2020, the market of biocrude in 2019 was 331 million with the compound annual growth rate of 4.5%. The last product from pyrolysis process is biochar. Based on the biochar figure, the major application for biochar was in the agriculture industry and livestock, which contribute a total of 43.97% of the total share. According to Inwood Research 2019, The global market of biochar was estimated to grow with a CAGR of 13.57% by the revenue and 11.22% in terms of volume. These are the two products of modified Solvay process. Based on maximized market research 2019, sodium carbonate had been widely used in factories and households to remove hardness from water and change the pH of water. According to the article by D.S. Peswire, the world sodium carbonate market size is expected to reach 16,650 million USD by 2026 at a CAGR of 1.4%. The last product is calcium chloride. Based on the report of Market Research Future 2021, it is expected to generate profitable opportunities for market competitors as the number of potential applications in industry, such as water treatment, agriculture, construction, and animal sterilization increases. According to expert market research in 2020, the world calcium chloride market has achieved a value of 1.42 billion USD due to the increased product utilization for de-icing and dust control, also rapid technological advancement. The next part is plant location selection. There will be 12 factors that been considered into this selection, which are availability of raw material, market availability, energy and power availability, climate suitability, availability of infrastructure facilities, social infrastructure, site characteristic, transportation facilities, flood and fire protection, labor availability, waste disposal facilities, and the last one, government policy and legal research. Three potential locations are selected for evaluation and comparison, which are Sungai Udang Melaka, Pengerang Johor, and Keteh Terengganu. This table summarizes the criteria evaluation that be made on those three potential locations. Based on the comparison and evaluation performed, where weightages are assigned to each factor and location, which 5 marks indicate very good and 1 mark indicate very bad. In conclusion, it is determined that Pengerang Johor is the most suitable plant location as it contains extensive infrastructure. That's from me. I shall pass the floor to Frederick.
Thank you very much, Shazani. Building on his presentation, this section, Conceptual Design, includes the screening of several process routes, preliminary mass balance and economic potential calculation, as well as process description. The screening is split into two sections, namely oily sludge recovery and chloride recovery. Two process routes are evaluated here for each of these sections. For the oily sludge recovery section, the first route is gasification. Gasification involves the use of steam and air to decompose the oil and sludge into syngas, which comprises of hydrogen, carbon monoxide, carbon dioxide, as well as char via partial oxidation and steam gasification reactions. The solid products are then removed using a cyclone separator, and the gaseous products enter the scrubber to remove any sulfide components using water. The resultant clean gas enters another reactor for water gas shift and methanation reactions as illustrated by these two equations respectively. The syngas products are then separated to its individual components using a pressure swing adsorption column. Overall, gasification utilizes steam and oxygen to convert oil and sludge into syngas and char via these four major blocks. The second route for oily sludge recovery is pyrolysis. In a pyrolysis reactor, the oil and sludge are thermally decomposed in the absence of air to form syngas, biocrude, and char. The solid char is discharged via a cyclone separator while the syngas and biocrude goes through a condenser to condense and remove the oil from the gaseous products. Subsequently, the syngas products are separated to their individual components via a multi-stage membrane separator. Next, we shall review two design alternatives for chloride recovery. The first alternative is the modified Solvay process, where a concentrated salt solution must be obtained first via a multi-stage evaporation of dilute salt water. The brine is fed into a bubble column reactor along with limited calcium oxide and excess carbon dioxide to form sodium bicarbonate and calcium chloride. Subsequently, the products are separated using a filter. The sodium bicarbonate undergoes the calcination reaction to be cracked into soda ash. Secondly, the salt cake and chlorine production route for chloride recovery is discussed here. Initially, solid salt reacts with sulfur trioxide gas made in situ to form salt cake, sulfur dioxide, and chlorine gas. The solid salt cake is removed while the gaseous products enter a reactor to partially oxidize the sulfur dioxide into sulfur trioxide. Subsequently, dilute sulfuric acid is used to absorb the sulfur trioxide gas, leaving chlorine gas escaping as a product. The sulfur trioxide is then recovered into the reactor via an oleum still unit. Now, this table summarizes the pros and cons for each process route. The gasification reaction utilizes steam and oxygen to convert oily sludge into syngas and char at 800 degrees Celsius and 1 atm. The main advantage of gasification over pyrolysis is that it has been widely practiced on an industrial scale and proven successful. However, additional raw material required for the reaction at elevated temperature yield higher OPEX, and the additional reaction system require more equipment, which increases the capex and make gasification less attractive in comparison. Pyrolysis, on the other hand, does not require the addition of raw material in a reaction. The decomposition of oily sludge into syngas, biocrude, and char takes place at 500 degrees Celsius and 1 atm. The main advantage of pyrolysis include the formation of a wide variety of valuable products, and moreover, pyrolysis grants flexibility in the product yield following market changes, which can be done by altering the reaction temperature and residence time. Perhaps the only drawback of this route is that it has not been industrially established, though recent events pointed out that mega corporations such as ExxonMobil is planning on a joint venture with Agilyx to start up a pyrolysis plant. From this brief evaluation, it has been decided that pyrolysis will be the selected route for this design as it yields favorable economic potential over gasification. Moving on, the comparison for chloride recovery routes is tabulated. The modified Solvay reaction occurs at ambient condition, converting brine with carbon dioxide and calcium oxide to form soda ash and calcium chloride. The main advantages of this technology include mild operating conditions, and that the CO2 can be obtained from waste flue gas streams, which contributes greatly to a greener road since it is designed for carbon dioxide capturing. However, the downsides are low conversion of salt at 35%, which may be overcome by recycling, and that it has only been proven successful experimentally in lab scale. In contrast, the industrially established route converts sodium chloride and sulfur trioxide gas into highly valuable salt cake and chlorine at 450 degrees Celsius and 1 atm in the presence of vanadium catalyst. However, the energy-intensive steps in recovering sulfur trioxide gas and the usage of hazardous components make this route undesirable. Moreover, this process requires dry solid salt as feed, which means all the water in the effluent streams must be removed, which is highly unlikely. In summary, the modified Solvay process was shortlisted as the design alternative for chloride recovery. Now I shall present Fastly to continue on with the preliminary mass balance calculation for the selected route.
Thank you, Frederick. Due to the time constraint, only the major equipment will be explained in the manual mass balance section. The first major equipment selected is API separator. Based on the research paper written by Yu and his colleague, the percentage of oil and suspended solid removed using API separators are 99% and 68% respectively. From the table, 99% of oil from stream 1 and 2, equivalent to 28.12 kg per hour, is removed to stream 3, leaving only 0.28 kg per hour in stream 4. The same goes to suspended solid, where 68%, which is equivalent to 2.19 kg per hour, is removed to stream 8, leaving only 1.03 kg per hour in stream 4. The second equipment is dissolved air flotation, which is used to further remove oil and suspended solid from the outlet stream of previous equipment. DAF is capable of removing 99% of oil and 56% of suspended solid. The calculated oil and suspended solid removed in stream 9 is 0.27 and 0.58 kg per hour respectively, leaving 0.01 of oil and 0.5 of suspended solid only in stream 7. For pyrolysis process, the conversion of sludge and oil to syngas, biochar and biooil is 100%, leaving no trace of them in the outlet of the reactor. Since phenol presents in biooil as methyl substitute phenols, the amount of phenol in the outlet becomes zero. Biochar acts as a sulfide absorbent, explaining the reason why sulfide is absent in stream 19. The selectivity of pyrolysis reactor is considered 1 since there is no undesired byproduct formed during the reaction. The yield of products from pyrolysis process, however, depends on the operating temperature of the reactor. Although it can be predicted using complex analytic calculation, the simplest way to determine the yield is through simulating the pyrolysis reaction. In modified Solvay process, the reaction between sodium chloride, carbon dioxide and calcium hydroxide produce calcium bicarbonate and calcium chloride. The calcium bicarbonate is further heated to form the end product calcium carbonate. Between the three reactants, calcium hydroxide is the limiting reactant, thus the manual calculation will use calcium hydroxide as the reference. Based on the stoichiometric of the chemical formula, the theoretical maximum value of sodium bicarbonate and calcium chloride produced are 1.22 and 2.43 kmol per hour respectively. Since the actual amount of sodium carbonate and calcium chloride produced are 1.12 and 2.14 kmol per hour respectively, the yield for sodium carbonate is 91.8% and for the calcium chloride the yield is 88.07%. In this calculation, it was assumed that only 66.67% of the calcium hydroxide reacted, since there is 60 kg per hour of unreacted calcium hydroxide in the outlet stream. Moving next is the comparison between manual mass balance calculation and mass balance calculated using simulation software. The difference between manual and simulation calculation for wastewater treatment inlet is 0% since both methods starts with the same initial value. The outlet, however, shows a difference of 10.01%. For pyrolysis section, the difference for inlet and outlet is 0.34% and 0.37% respectively. The inlet for Solvay process shows difference of 4.65%, while the difference for the outlet is 5.32%. The difference between manual calculation and simulation results can be attributed to the property models that is used in the simulation software. The final treated wastewater also meets the discharge standard based on the Environmental Quality Industrial Effluents Regulation 2009. For this project, standard B is used as reference since the discharge point is assumed to be located downstream. I will pass the time now to the next presenter, Teresaline, to explain the economic potential.
Thank you. Next, I will elaborate on the economic potential of this project. As you can see here, there are two major raw chemicals used in this plant, and both are fed into the Solvay process, which produce sodium carbonate and calcium chloride using the recovered chloride from the wastewater effluent. From the mass balance, the final mass flow for calcium oxide is 86.63 kg per hour, times with 8,400 hours of operation per year, we got 727,692 kg per year. And according to Alibaba, the commercial price for calcium oxide is 0.31 ringgit per kilogram. Hence, the annual cost for calcium oxide is 225,584.52 ringgit. By using the same manual calculation for carbon dioxide, the total annual cost is about 2.5 million per year, and summing up both prices, the total annual raw chemical cost for this project is 2,780,521.73 ringgit. For the products, the project is expected to produce 8 value-added products, which includes syngas, consisting hydrogen, carbon monoxide, carbon dioxide, methane gas, as well as biocrude, biochar, sodium carbonate, and calcium chloride. Total up everything we got about 13,358,736 ringgit. And here's the manual calculation of the economic potential. EP1 considering only the raw material cost, we got about 10.5 million revenue, while after considering the annual utilities, the revenue of EP2 is about 6.2 million per year before heat integration, and after heat integration, we can reduce the usage of utility by adding 3 heat exchangers in the plant, and now we have an estimated revenue of 7.9 million ringgit per year. And that is all for economic potential. My friend Jared will explain the next part, which is the process flow diagram.
So now I'll be talking about the process flow diagram. So this is the overall process flow diagram for our design. This design is separated into 3 main processes, which starts off with the wastewater treatment, where I'll be talking about the physical separation, and follow up by the pyrolysis process, where sludge is converted into syngas, biocrude and biochar, and the Solvay process, where the chloride is converted into sodium carbonate and calcium chloride. Let's start off with the wastewater treatment. First of all, the oily water and the ballast water goes through an API separator, where the oil and sludge is then separated via gravity, where the oil is transported to the pyrolysis reactor and the sludge is transferred to the sludge holding tank, and the remaining solution will then be transferred to the DAF separator. In the DAF separator, the remaining sludge and oil component which has gone through the flocculation will then be further removed by adding air into the vessel. The sludge will submerge to the bottom of the tank and then be transported to the sludge holding tank, whereby the remaining solution will then be transported into the sedimentation tank. Next, in the pyrolysis process, the sludge and oil from the wastewater treatment process goes through a reactor at 500 degrees and 1 atm to be decomposed without oxygen. The products are then discharged into a cyclone, where the vapor phase containing syngas and bio-oil escape at the top stream, while the solid char exits at the bottom of the cyclone and stored. The top vapor stream is cooled, where the biocrude is condensed and stored, while the syngas is further separated to its respective component using multiple stages of membrane filter. Lastly, in the modified Solvay process, ammonia is not included in the reaction, where calcium hydroxide is being used to provide an alkali-based environment for the reaction to occur inside the bubble column reactor. A double ion exchange reaction occurs in the bubble column reactor, whereby the sodium ion captures the bicarbonate ion, forming a baking soda, while the calcium ion combines with the chloride ion, forming calcium chloride as shown in the equation here, and the NaHCO3 is then refiltered and calcinated to yield soda ash, while the calcium chloride is dried and stored. After combining the processes, this will be the final PFT for the overall process before heat integration is done. So now I'll pass the floor to Terry to talk about the heat integration process for design.
Thank you, Jared. Now we are moving on to the heat integration part. The first step in heat integration is the identification of hot and cold streams. As for this project, we selected 4 streams in Solvay's process for analysis, which include the calcium chloride at stream 66, sodium carbonate at stream 58 as cold streams, and sodium carbonate moisture at stream 62, and carbon dioxide stream at stream 55 as hot streams. The total duty for all these streams is 3175.71 kilowatt, and for the adjusted temperature, we are using delta temperature minimum value of 20 degrees Celsius. Moving on to the second step, this is the heat cascade for the potential heat exchange between the streams. For this cascade, it is stated that a heating utility is needed to accommodate the heat integration with the value of 222.32 kilowatt. Here's the composite curve showing the heat recovery, which is the bounded area between the hot and cold streams, while the value of required heating is shown by the difference of X value between the hot and cold streams. And this is the grand composite curve with beta summation of the required heating, which is 222.32 kilowatt, as well as the pinch temperature of 273.13 Kelvin. And the final step is to develop a heat exchange network between these four streams. From this network, we can see there are 3 heat exchangers required with 1 heater for the heat integration. The first heat exchanger is used to exchange heat between stream 58 to stream 62, and the second heat exchanger is used to exchange heat between stream 66 and stream 55, and the third one is used to exchange from stream 66 to stream 62, and finally an extra heater is required to complete the heating of stream 66 to temperature of 375.23 Kelvin. And this is the process flow diagram after heat integration. Zooming into the Solvay process unit, you can see here there are 3 heat exchangers and 1 heater with the duty of 222.33 kW to complete the heat integration. After computing both process units, a total of 2,953.38 kW energy can be saved. Then a modified simulation flowsheet was developed for the process after heat integration, and we extracted the estimated cost from the economic activation of the Aspen Plus simulation. Before the heat integration, the estimated utility is about 4.4 million ringgit, and after heat integration, the utility is reduced to about 2.7 million ringgit with almost 50% utility reduction. And that is all for heat integration. Next, I pass this floor to my friend Frederick to explain the process instrumentation and control strategy for this project.
Thank you, Terry. Moving on, I shall now demonstrate the application of various control schemes implemented in this design, namely cascade control, feed-forward ratio control, split range control, as well as override selective control. In the equalization tank T105, a selective control is implemented to maintain a minimum level in the tank as well as a minimum flow of slurry at the discharge line. During normal operation, the level controller adjusts the slurry exit flow by changing the pump speed. The slurry velocity at the discharge line must always be kept above a minimum value to prevent the line from plugging. Thus, a selective control is designed so that as the flow at the exit line approaches the lower limit, the flow controller takes over and speeds up the pump. This is done by using a high selector and a reverse acting flow controller with a high gain. The set point and the gain of the flow controller are chosen so that the controller output is at the maximum value when the measured flow is near the constraint. Besides that, the cascade and override control schemes may be demonstrated in the reactor R201 to maintain the reactor bed level and as a safety precaution respectively. Superficial gas velocity, SGV, is a supercritical parameter that affects the health of a fluidized bed reactor. SGV is basically the gas velocity at a reactor distribution plate. A high SGV increases the fluid bed level, which increases the likelihood of forming sheets at the reactor dome, while a low SGV decreases the reactor bed level, causing reaction to be highly concentrated at the bottom section of the reactor, which tends to create hot spots or chunks, resulting in a reactor shutdown. A sudden spike in temperature may indicate the formation of sheets or chunks in the reactor. Thus, to avoid such incident, an override control is used where multiple redundant temperature probes are installed at several locations of the reactor. If any of the temperature reading reaches the upper constraint, the high selector takes that signal only and sends to the override temperature controller, which then adjusts the inlet nitrogen flow rate so that the bed level and temperature change accordingly. This safety system allows nitrogen to bypass the heater and enter the reactor at ambient temperature which act as both a cooling agent and a bed level manipulator. Furthermore, a cascade control strategy is also implemented where the level control acts as a master while the flow control is the slave. The level transmitter measures the bed level and sends the signal to the level controller where a set point is specified. The level controller calculates the error and then outputs a set point for the flow controller, which then adjusts the inlet gas flow rate accordingly. Lastly, a hybrid feed-forward ratio split-range control scheme is implemented at the premixer to ensure an optimum pH for the Solvay reaction to occur. A ratio control is used to ensure a specific molar ratio of brine solution to calcium oxide is maintained. The analyzers installed at stream 41 and stream 50 measure the composition of brine and output signals to the ratio station. The ratio station then splits its output signal to manipulate either the flow of the brine or the calcium oxide to maintain the desired pH in the mixer. Here is a snapshot of the full PNID, which can be found as well in the technical report and the drawing files. Overall, the control systems are in place to ensure a safe and healthy operation of each equipment as well as the plant as a whole. I shall now invite Jared to present on the HAZOP study.
Thank you, Fred. So now I'll be talking about the safety and loss prevention of our project. In this topic, I'll talk about the HAZOP based on the processes in this design, and my teammate Terry will be talking about the plant layout for our project. So for the HAZOP studies in this design, we selected these three study notes, which involves all three main equipments of each process, which is the DAF unit in wastewater treatment and the reactors for pyrolysis and Solvay process. The diagram shown here is the DAF unit, and the orange line indicates the stream which potentially brings harm to the process, which is the air supply from the compressor 101 and the feed solution inlet from the flocculation tank. For note 2, the stream involved will be the inlet sodium chloride solution supply stream from the heat exchanger E202, E203 or E205, and the outlet product stream to the cyclone over here. In the modified Solvay process, the stream involved will be the inlet supply stream from the mixer, which is this, and the outlet product stream to the cyclone, which is this stream. So here is an example of the HAZOP study, which is done based on the NOT3 reactor in Solvay process. In terms of flow, there are three possible scenarios. There will be no flow, less flow, or more flow. And each deviation will either caused by the leakage, blockage of pipeline, or the failure of controller, which will also lead to low yield of product or overpressure when there is overflow occurring. So to mitigate this problem, emergency alarms such as level alarms are to be installed and proper regular maintenance are to be applied. In terms of temperature, it will be most likely be deviated to either low temperature or high temperature due to malfunctioning of controller or heater. This will bring consequences such as overheating of reactor and or overpressure, which may cause or lead to explosion. Emergency alarms such as temperature alarm and pressure valve should be installed to prevent this. Lastly, as mentioned just now, the pressure of the reactor will also increase due to the flow of temperature. Therefore, an emergency alarm such as the pressure alarm and relief valve are to be installed to mitigate this problem. So now I'll pass the floor to Terry to talk about the plant layout.
For the plant layout, the area is divided into three parts: process area, utilities and off-site, and non-plant buildings. There are three main process areas of this plant: A1 effluent treatment, A2 Solvays, and A3 pyrolysis process unit. For this layout design, the process areas, especially Solvays and pyrolysis with high hazard potential, are located almost to the center of the plant to allow evacuation in case there is any emergency. Meanwhile, for the utility and off-site, all of these units revolve around the main process area to ease the access, as utilities are required in order for the main process area to operate. For the non-plant building, The facilities such as cafe, admin, parking lot, and medical care are located near the main gate to ease the workers to enter and exit the plant area, and they are also located away from the main process area to limit the hazard exposure. And the loading area C11 is located between the product storage and export terminal to ease the export of the product. And there are 3 gates in total for this plant. G1 is the main gate to workers and personnel to move inside and outside the plant, and G2 is the import gate. It is for raw material and utilities transfer into the plant, and G3 or the export gate is for the product export outside of the plant.
Thank you, Teresaline. Now I will highlight the major takeaways from this presentation. The objective of this plant design is first, to ensure the final treated wastewater meets the discharge limit set by the government, and second, the recovered material from the wastewater is to be converted into value-added product. In this case study, the industrial effluent consists of oily water, oily surface water, and ballast water which contain high BOD and COD due to the presence of oil and other organic compound. The removal of oil and suspended solid are done using API separator and dissolved air flotation unit. The recovered oil produces syngas, biochar, and bio-oil. Sodium chloride is recovered from the wastewater and processed into calcium chloride and calcium carbonate through modified Solvay process. Overall, it can be said that this plant design managed to achieve its objective by satisfying the discharge limit stated in Environmental Quality Industrial Effluents Regulation 2009 for Standard B. Furthermore, the calculated economic potential of this plant are 6.05 million ringgit, indicating that the value-added product is feasible and profitable to be produced. The EP shows an increase up to 7.74 million ringgit per year after the heat integration is applied. And with that, we have come to the end of our group presentation. Thank you for listening. Have a nice day. Till we meet again in the Q&A session.